So good morning. Today we are going to see another section in computer vision course. It's on face recognition. So basically we have a huge data set given. From that we have to identify face of one person. So it could be a surveillance kind of an application where somebody is there at the door, and automatically a camera takes the face, and it identifies whether this person is there in the database, already approved person. Then it will give the access to the person. So this is the typical kind of an application of a face recognition problem. So let us see how we can do this. So some simple approach could be just you take the mugshots of the face. Mugshot is basically you take the contours of your face and just record the gray level values of that face, and you construct a vector, and based on the vector you just try to compare that vector with the already existing database, and try to see whether the vector matches with the existing data set. So if it matches, then you say that this person is been recorded or recognized. So that is a simple approach. So what could be the problems with this? Usually the dimensionality of this face vector will be very large. That means you have to scan a 512 by 512 image and form a vector. That means it will be a very large vector. So if you compare this vector with already existing data sets, it will be a time consuming process. So how to reduce this, or this is a typical problem in any computer vision based applications. So we will go for a kind of dimensionality reduction. That means we will try to take the major components of this vector, and we will record those major components, and in the database also we will take the major components and then try to match. So any unnecessary data that we will avoid, and we will take only the necessary thing. So how we can do that? So you might have learned the concepts of eigenvectors and eigenvalues. So I don't want to repeat it, but just for completeness, let us see what is it. So A is a matrix, and it is acting on a vector x, and it produces another scalar multiple of the same x vector. So this is called a classical eigenvalue problem. So the vector x represents the data collected from the face, and we have formed a vector, and so the eigenvalues, basically the lambda, shows you the most prominent values of that vector. So in the beginning we were talking about how to take the important values from the given vector. So lambda should represent the important values, and we call this as an eigenvalue. So most prominent eigenvalues must be taken, and those vectors or those values will be recorded as a vector. So that is the problem. So this is a simple example. So A will be a 3 by 3 square matrix, and the lambda values computed from that is lambda 1 is 7, lambda 2 is 3, and lambda 3 is -1. So you can see the eigen values are 3 because we have a 3 by 3 matrix, and you can compute the eigenvectors from this. It's a standard eigenvalue computation problem. So x1, x2, x3 represents the eigenvectors. So how to compute the eigenvalues, that is being demonstrated in this slide. So you have to write a characteristic equation. So that is determinant of the matrix A minus the scalar multiple into the standard identity matrix, and you equate it to 0, then you can have a polynomial kind of an equation, and from that you can compute. You might have done this during your school days. So this is the procedure. So now the eigenvectors has been computed, and we have to find how we can go for face recognition problem. So let us say we have a long vector u, and so these are the intensity values basically. So this is the first pixel intensity I11 up to INN. So the entire m by n matrix will be scanned and stored in as a vector u, and for each phase, so we have a data set of different phases, and for each phases we have to take so let us say we have p persons. So for p persons we are constructing a matrix A. From that each phase we have a vector u1 up to un. So for all p we construct this A matrix, and then we go for a kind of a transpose matrix. So this is called a correlation matrix, and from this we are trying to find out the eigenvalues of this correlation matrix. So now the matrix U is represented as a combination of these eigenvectors. So from linear algebra you might have studied that you have a vector space, and you can actually squeeze this vector space in a smaller form by identifying all the basis vectors of this vector space. So phi i's are basically the basis vectors, and you can create any vector in this vector space by a linear combination of so ai's are the scalar multiples, and combinations of these will give you any vector that corresponds to this space. So this is a typical kind of a problem where maybe you can find out the eigenvalue. So this is the problem. So maybe in the next session we will try to identify how we can incorporate this in software, and we will see in the next class.